Now let's go back to the Streamline capture to explore the CPU and GPU counter activity in more detail. This helps us build up a picture of how the device handled the game's content as it passed through the different stages of geometry and pixel processing. Because we used a counter template to select what data to capture, we'll select this template again here to arrange the charts so it's easier to analyse. You can configure the charts in any way you like, but the templates give you a good starting point. We know that our problem is related to the GPU, but we can also check the CPU activity here. The CPU in this mid-range smartphone contains a mixture of small and efficient Cortex-A53 cores and large and powerful Cortex-A73 cores. Heavier tasks are handled by the more powerful cores, and smaller tasks by the more efficient cores. It's useful to check the activity across these cores to ensure that the workload is split across threads. If only one core is doing all the work, you're missing out on performance or energy efficiency. Let's look at the GPU usage. It's useful to check what frequency the GPU is running at. If we highlight a 1 second region here, we can see that the GPU is active for 949 million cycles per second. That's 949 MHz, which is the maximum frequency for the GPU in this device. On a higher-end device, this number might be much lower, as the GPU might have more shader cores, each running at a lower frequency to achieve the same output more efficiently. We know that the application is GPU bound, and we can see that here, where the GPU is active at the maximum frequency. GPU bound sections look like flat lines where there is no idle time. GPU active cycles is approximately equal to the fragment work queue, showing that the fragment activity is the heaviest workload. Let's look a little closer. Fragment and non-fragment workloads should always overlap. If you see areas where one queue goes idle while the other is active, you could have a serialization problem. This can happen where there are data dependencies. Vulkan applications can suffer from this, as described in the previous module. The Mali geometry usage and Mali geometry culling rate charts show how efficiently the GPU is processing geometry. Here we can see how many primitives are sent to the GPU, how many of them are discarded during geometry processing, and how many actually end up on screen. In the selected time frame, around 1.2 million primitives entered geometry processing, but around 800,000 are culled at this stage. Work that is culled at this stage is not passed through to pixel processing, so this is good news, but it would be better to organise the content so that non-visible primitives are not passed in at all. Here we can see why primitives were culled. Around half are culled by the facing test, which is expected because these are the back-facing triangles of our 3D objects. What is more concerning is that over 33% of primitives were culled by the sample test. The sample test discards primitives that are too small to be rasterized. These primitives don't hit any sample points and are therefore considered invisible. Ideally, this number should be less than 5%. This can happen when complex objects are positioned far away from the camera and triangles in the mesh are too small to be visible. Higher numbers here could indicate that the game object meshes are too complex for their position on screen, and you should look at using mesh level of detail to simplify the meshes when objects are further away. This problem gets worse if you have primitives that are large enough to pass the sample test, but still only cover a few pixels. This is where we see problems with microtriangles, described in the previous module. To check if we have a problem with microtriangles, we can look at the Mali core workload property chart. Here we can see the partial coverage rate, which indicates how much pixel processing work is being done where some samples are missing. Ideally, this should be less than 10%. In some sections of this game, the partial coverage rate is very high, more than 60%. This suggests that the content does have a high density of microtriangles, so we should investigate our meshes to see if we can simplify them. It's always worth checking how the game is using early and late ZS testing to discard pixels that are hidden by other objects or stencil masks. early ZS testing is relatively inexpensive because it happens before any pixels are coloured in by fragment shading. To get the benefit of early ZS, your application must pass in geometry in a front-to-back render order, starting at the point closest to the camera and moving further away. The late ZS test handles any work that could not be processed before fragment shading. For example, if a shader programmatically modifies GL frag depth, early ZS testing cannot be used, and late ZS testing is forced. Because late ZS testing happens after all the fragment shading work has been done, it is expensive and should be avoided. Streamline provides a range of charts to help you analyse shader behaviour. The Mali core unit utilisation chart shows the percentage utilisation of the functional units inside the shader core, the execution engine, the varying unit, the texture unit, and the load store unit. To improve performance, you should try to reduce load on the most heavily utilised functional unit, in this case the execution engine, although reducing load on any of the units is good for energy efficiency. Through the Performance Advisor report, we learned that our shaders were too computationally expensive and that we could benefit from reducing the precision. In Streamline, we can use the Mali varying usage chart to see the number of cycles where 16-bit medium precision or 32-bit high precision interpolation is active. Here we can see that 32-bit interpolation is used in most cycles. 16-bit variables interpolate twice as fast as 32-bit variables and use half the space in shader registers to store interpolation results, so it's recommended to use medium P 16-bit varying inputs to fragment shaders whenever possible. We don't have time to show you all the charts available in Streamline, but there are many more to explore, such as those that help you diagnose texturing or memory bandwidth problems. You can find documentation for all the performance counter data that Streamline can collect on the ARM developer website. Streamline has helped us to identify a problem with microtriangles and confirmed some of the shader problems indicated by Performance Advisor. Next, we will take a look at the Gaming Graphics Analyzer to see if we can find out which object meshes might be too complex for their position on screen.